All right, what's going on, you guys? Another LeetCode problem today. This one's called subsets. We're given an integer array nums of unique elements. They want us to return all the possible subsets or the power set of the integer array that they give us. So our solution cannot contain duplicate subsets, and then the answer can also be in any order. So if they give us this input set 1, 2, 3, they just want us to form all possible subsets of this set. So, and again, that's going to be the power set. So for 1, 2, 3, we can see, the empty set, that counts. That's always going to be a subset. And then we have each element by itself, right? 1, 2, and then 3 over here. And then we have every combination of two elements. So 1, 2, 1, 3, 2, 3, and then finally, just all of those. The actual set itself is also a subset. So 1, 2, 3. So that's going to be 8 subsets for a set containing 3 elements. So thinking about that can help us derive a solution. So just coming up with an algorithm or a formula that tells us, okay, how many subsets can we form with any given set, based on the size of that set. Well, the formula for that is going to be the number of subsets we're going to have. We'll just call that S, is going to be 2 to the n, where n is the number of elements in that input set. So just to confirm that, or to test it, really not really much of a proof, but if we look at this set nums, we see there's 3 elements in there. So if we do 2 to the 3, that gives us 8, and there's going to be 8 subsets here. So similarly, this second example only has 1 element in the set, so 2 to the 1 is just going to be 2, right? So, and there's 2 subsets here. So anyways, the way we're going to do this is we're going to use recursive backtracking. So we'd basically, we would start out with, we'd seed our recursion with, an empty set and an index, right? So an index I, which would just be 0 at first. So let me label that. So this 0 is going to correspond to an index I, and and basically in the elements it gives us. So, and I believe it's called nums. So that I is going to correspond to an index in nums. And then this is just a subset. So we're going to have a couple recursive calls. So, the first call is we're basically going to use I. So I is 0 at first. We're going to increment I with each recursive call, and then add, that element that we increment, basically the element corresponding to I in nums, we're going to add that to the subset in the next recursive call, like this. So we would add 1, and we just increased I to 1. Okay, and then this is where backtracking comes in. So we're actually going to pop whatever element is that we just added before we do the next recursive call. So, I mean, really, technically, the order this code would execute is we keep going down like we do a depth first search as far as we can go left, but I'm going to cover the backtracking first because it makes a little more sense to me when I do it this way. So, so we would backtrack, we'd pop the 1, and then in the next recursive call, in this level of our recursion, we would put a 2 into the set, and we'd increment I again, so I would be 2. And the reason there's no 1 there is because we backtracked before we called the recursion. This way we popped that 1. So we're going to do the same thing actually here. So we're going to backtrack a 3rd time, because we're going to backtrack basically as many times as I can iterate up to the size of nums. So the size of nums in this case is 3. So there's 3 3 recursive calls really. So we're going to push that. We're going to pop the 2 from backtracking. We're going to push a 3 to that subset, and I would be incremented to 3. So we basically do the same thing, recursively for all of these. So for this 1, we would first add a 2, right? So we're gonna add a 2 there, and then we would also increment that I to 2. We need to backtrack, so we'd pop the 2, right, in the next call. We'd pop the 2, and then we'd add a 3, incrementing I from 2 to 3. Okay, and then for this, we're gonna add a 3, right? Increment that 2 to 3 for I. Okay, and then let's see, we can't do any backtracking here because notice this I is 3, so there's nowhere to go on this path because our I is the same size as, or it's equal to the value of the size of nums, right? So there's nowhere to go that way. But we are going to keep backtracking here. Also, we can't go anywhere here, right? Because it's this 3. That's what indicates that we're stopping. But we can go this way, so we could actually add a 3 there, and we would increment this I to 3, so that indicates again that we stop. So we can see that we're stopping here whenever I is 3. Let's just indicate that. And then these, all along the way, we would have been adding these subsets to our result vector of sets, right? And then notice also how many sets we just created. We created 1, 2, 3, 4, 5, 6, 7, 8 sets, which is exactly the right number for an input size of 3 elements, right? Our input array here was 1, 2, 3. So in terms of the time and space complexity, the time complexity, we're gonna have, so I'll just say T for time. We're gonna have big O of 2 to the n, basically nodes in our recursive tree, right? So it's going to take big O of 2 to the n time, where n is the number of elements in our input vector. And then for the space complexity, we're just going to have big O of n, where n is the number, again, the number of elements in our input vector. And that's because for the recursive call stack, we're going to have a space that's proportional to the height of the tree, and how many nodes are in the tree, right? There's 2 n nodes in the tree, and how do you calculate the height of a binary tree? Well, you take log base 2 of the number of nodes, right? So this 2 is going to cancel out, and it's just going to give us n. So the space is big O of n. Okay, so yeah, let's just get into the code here. So we're gonna have to first have a vector of vectors for that result, for the result, right? And there's gonna be 0 vectors in there at first, so I'll specify that as by passing in a 0 there. We're also going to need a vector for the current subset that we're looking at. So I'll call the subset, and then there's going to be 0 elements in that at first as well. We need to seed our backtracking, so I'll just do a function overload on subsets for the backtracking, and then we just return res at the end of all of that. So let's write this function overload for our recursion, for our backtracking recursion. So it'll be void, we'll just call it subsets again, but it's going to take more parameters, right? So we need that result parameter. That's going to be by a vector of integers by reference. We also need the nums array, right? This is the input array, and then we need the current subset that we're looking at. So that's going to be a vector of integers by reference. So we'll call that subset. And then finally, we need that integer index. That's not going to be by reference. That the scope of that is dependent on the actual recursive call that it's in. So that integer will not be by reference. Okay, so yeah, let's go ahead and seed this. So we're passing in res, subset, nums, and then I, which is just going to be 0 at first. So the first thing we want to do is push that subset back into the result vector. And once we've done that, we're going to iterate from j, or from I all the way to nums.size, right? And we'll use j as our iterator, since I is basically telling us where to start in the loop for each recursive call. So so we're going to increment j with j++, and then so first we want to push, so we're going to do subset dot push back to add the next element in the nums array, so nums j, to the current subset that we're building. And then we're going to seed that recursion. So we'll do subsets, or not seed it, but continue it rather. So by passing in res subset with the element we just added to that subset, the same nums array, and then we're going to increment our index by 1. And the new index we're passing in is going to be wherever we are in this loop. So it's going to be j, not I. So that's an important difference. So it's going to be j for the within the loop. Okay, and then after we call that recursion, remember we've got to backtrack. So and this is why it's called a backtracking problem. We're going to do subset.pop back, basically to get rid of whatever element we just added, like I showed in the whiteboarding. So this is pretty much it. This is all the code. It's not very much. So now I'll just go ahead and submit this. So yeah, hopefully this video helped you understand subsets a little bit better and give you a good intro to backtracking. If it did, leave a like and subscribe. I'll see you guys in the next video. Peace.